All right, class, welcome to Structural Kinesiology. This is Module 1, the Foundations of Structural Kinesiology. So what is kinesiology? So kinesiology is an interdisciplinary study of human movement. It integrates anatomy, physiology, and biomechanics. And then as a discipline, it is a recognized academic field, prepares students for clinical and performance careers. So careers such as clinical exercise physiologist, which is what I am. You can go into physical therapy, occupational therapy, athletic training, various, and then kinesiology can potentially diverse more into nutrition, go and become a dietitian, go and become furthering into that field. There are various different types of ranges within this discipline. So what is structural kinesiology? That is what we're going to be focusing on for this term. So it focuses on musculoskeletal system and how the structure influences movement. So how the body is moving, why it's moving, and what is happening. So why this matters? So we can use structural kinesiology for exercise analysis to be able to analyze certain movements. So a squat or a jumping jack. Analyze what is happening at each joint within the muscles, how those joints are being innervated and moved, what needs to occur for those joints to become more efficient, to become stronger. And with that, we can do injury prevention. So especially as depending on what population you're going to be working with. So whether you're working with older adults, so trying to work on strengthening the stability type of muscles that we need for our daily activities of living. Or maybe again, structural kinesiology can be more for rehabilitation foundation. So whether there is an injury now, so how can we rebuild and provide more stability in an area where there is injury? So for this course, for this module today, we are going to be going over planes and axes, bones and joints, muscle structure, and then neuromuscular control. So these are our objectives for this course. So understanding different terminology, identifying the planes and axes, explaining muscle contraction principles. So first off, we need to understand anatomical position. This is the position that the body is in that we are going to be using to describe when we are describing various types of movements. So the anatomical position is when you are standing upright, arms at side, palms facing down or facing forward. So you see that example here. So why this matters? Because it helps standardize the movement description. So that way we're all on the same page. When I say, which we're going to get into, when I say anterior, posterior, lateral, contralateral, you're going to know what I'm talking about. When we are in the same anatomical position, you're going to understand what joint, what area I'm referring to. So here are some directional terms. So as I mentioned just a minute ago, anterior and posterior. So anterior is going to be front, posterior is going to be back. So when we are in that anatomical position, standing upright, arms by our side, palms facing upwards, the bicep is going to be anterior, so on the front, while the triceps are going to be posterior on the back. And then directional terms as well, we have medial and lateral. So medial is going to be towards the midline, while lateral is going to be away from the midline. So those can be very important, especially when different joints are being affected or different areas of the body are hurting. So maybe your knee is hurting, but maybe it hurts mainly on the lateral side, or maybe it's hurting more on the medial side. So, and that can infer, based off where that pain or that discomfort is, maybe which ligaments are being affected, which areas are going to be are the most what is happening. So that helps us understand what to potentially diagnose and treat. And then we have proximal and distal, so being able to describe where on the body these joints are. So proximal is going to be closer to the trunk, distal further away from the trunk. So for example, your elbow is going to be proximal compared to your wrist, because the elbow is closer to your trunk than your wrist. And then we also have superficial and deep. So superficial being near the surface, and then deep being further away from the surface. We have ipsilateral and contralateral. So ipsilateral means the same side. So this is a very common term, especially, for example, if someone has a stroke. If they are affected on one side of the body, if the stroke was severe enough where it affected their movements, so it affects their left side. So maybe they have their left arm is affected, and then you can say their ipsilateral leg is affected as well, or their left leg on the same side. And then contralateral is going to be opposite sides. So this can be seen, or this is an example. So if someone is having knee pain, they may shift their weight to the contralateral side to reduce the pressure on that joint that is causing that discomfort. So contralateral, opposite side. So knowledge check. Describe the bicep location using two directional terms that we just reviewed here. So anterior, posterior, proximal, distal, superficial, deep, etc. So how would you describe the bicep, or how can you describe the bicep? And then we have planes of motion here. So we have 3 different planes of motion. So sagittal, frontal, and transverse. The sagittal plane of motion is the plane where you see extension and flexion movements. So for example, with the shoulder, with the shoulder joint, to be able to flex the shoulder joint, you're raising the arm up, and then to extend it, raising it down and back. So that is the sagittal plane. It cuts the body into kind of left and right, like a plane going in between your head, kind of cutting it left and right. And so it's moving along that plane. And then we have frontal, which involves abduction and adduction movements. So abduction is taking something away, going away from the body, and then adduction, bringing it back towards the body. So frontal divides the body into front and back portions. We have a picture in a second to kind of tie over what this means. But so to divide it into front and back, you're going along that plane, and then transverse is dividing the body into front and lower, or upper and lower halves. So you'll have rotational movements at that plane. So here is the illustration of that. So you see here we go. You have the sagittal plane is right here. So this like big plane here. Oh goodness, here we go. That's cutting the body into that left and right motion. So again, that's going to be where you see you're going to have the flexion and extension going along that plane. And then we have the frontal plane, this big one here, that's dividing it it's dividing it into front and back halves of the body. So that plane involves abduction or adduction movements. And then this transverse plane dividing the body into that upper and lower portion where you have those rotational movements. So here is an example of these planes in motion. So for lunging, you are having to flex and extend the hip and the knee. So because there's flexion and extension, we have it in the sagittal plane there. And then and then in the frontal plane over here, to be able to do lateral raises, you're abducting away, taking it away, and then adducting it back, going in that frontal plane of motion there. And then maybe doing like Russian twist or something similar, holding that dumbbell there and twisting, going back and forth, having that 2 opposite motions within the top. Your body's being divided into upper and lower portions. So we have that transverse plane. So knowledge check. So what are the planes for a push-up? So for a push-up, you are having to flex and extend your arms in the push-up. So what range of motion involves flexion and extension? And then jumping jack. So for a jumping jack, we are having to move our arms away from us and then back together. So abduction and adduction. So what plane involves those movements? So within the planes, we have axis of rotation. So the axis of rotation is going to be perpendicular to the plane, and that's where you're going to be able to see the movement of the joint occur. So again, what is going to be perpendicular to the plane of movement? So for the sagittal plane, so for flexion or elbow flexion, going up and down into that sagittal plane, the frontal or the medial lateral is going to be the axis. And then we have frontal plane, for something moving in the frontal plane going out and together, that axis is going to be at the sagittal axis. And then something moving in the transverse plane, so rotating, is going to be along the vertical or longitudinal axis. So see here we go. So here is an illustration to help kind of bring that relationship all together. So you have the planes. So we have the sagittal plane. So again, it's dividing the body into that front and half location. And then the axis is perpendicular to it. So you have, oh, sorry, I said this wrong, the frontal plane, sorry, and then the sagittal axis. And then we have the longitudinal axis along the transverse plane. And then we have the transverse axis along the sagittal plane. So common confusion, plane versus axis. So movement occurs along the plane while rotation occurs along the axis. And again, honing in, the axis is perpendicular to the plane. So for example, with a squat, you are flexing and extending the hip and the knees. That is in the sagittal plane with flexion and extension. And so the axis of rotation for those joints, for it to allow those movement, is going to be around the frontal axis, what's going to be perpendicular. So again, holding in, plane is a direction of movement, while the axis is a line of rotation. So here is a knowledge check. So, and I've included a picture here to help you see all of the planes as long as the axis in one illustration here. So which axis for squat movement? Again, with the squat, you are having flexion and extension of the hip and the knees having to go down and up. So with what plane is there flexion and extension? Where does that occur? And then once you determine what that plane is, what is the perpendicular axis? Where is that going to happen? Where is that rotation occurring? All right, and now we're going into our bone classification. So overview, we have various types of bones within our body. We have long, short, flat, irregular, and sesamoid bones. They all have a different purpose, whether that some of them are going to be for stability or protection, or some of them are going to help with assisting movements like different gliding movements. And then joints within the body, so what connects our bones together. There are 3 different types of joints. We have fibrous. So the fibrous allow little to no movement and primarily serve for protection. You'll see this along our skull line, so along the suture lines within our skull plates. So example right here in this first picture. And then cartilaginous joints, these are going to allow limited movement and primarily help serve for shock absorption. So you'll see this in costochondral joints, which is where the bony portions of our ribs are connecting to their respective costocartilage. So you see that in this area here. So the cartilage connecting to the ribs coming out here. So this area, this is cartilaginous joints. And then we have synovial joints, which is the most functional, important joint that we're going to discuss here within the realms of kinesiology, because they are freely movable and they allow for a wide range of movements. However, that can come with a cost where there is going to be an increased risk of injury. And so understanding the different types of synovial joints, how those joints are able to move, how those joints function, can help you understand for injury prevention or rehabilitation. So a synovial joint in particular is going to have that synovial membrane, that capsule, synovial fluid, and that's going over here as well. So you'll have the joint capsule with synovial fluid and ligaments coming off of that joint. So those are the characteristics of a synovial joint. And then there are various types of synovial joints. We have a hinge joint. So a hinge, let's see, we have it over here. The hinge joint is going to allow bending and straightening only in one plane. So much like a door hinge. So you'll see that in the elbow, in the knees, and the ankle joints. So only in one plane of motion. And then you have your pivot joint. So that's going to be right here, your pivot joint. So that allows for a rotational movement around a single axis. So the most common one is the atlantoaxial joint at the base of your neck. So it allows you, it's at the first vertebrae of your neck, allowing you to rotate and pivot your neck. And then we have ball and socket, which allows for the greatest range of motion in all direction. You see this in, my face here is in the way, but it's this joint down here. You see this in your hip and your shoulder areas. And then we have saddle, which allows movement in two planes, so going back and forth and side to side. So here we go, saddle. It's going to be a common one is at the metacarpal joint at the base of your thumb. So the thumb can go side to side, back and forth. So two planes of motion there. So adduction, so it can adduct and like abduct going away, adduct coming together. It can flex and extend. And then we have the condylar joint, which allows for angular movement in two planes, but prevents rotation. So right here, so that is going to be most commonly seen at the wrist. So again, we can, two planes of motion, like maybe we can flex and extend, we can adduct and adduct, take it away from the body, bringing it back in. We can rotate. However, the joint itself, like if I needed to rotate, I'm going to rotate the forearm, but the wrist itself is going to stay transfixed and it's not going to move. So it prevents rotation within the joint itself. And then we have plane or our gliding joints. So that is seen right here, most commonly within our intertarsal joints. So they allow limited sliding or gliding movements between flat articulating joints or surfaces. Alrighty, so now let's check what type of joint is the knee. So the knee, giving a hint, is of course going to be a synovial joint. It's going to have that joint capsule, synovial fluid, to help protect and lubricate the joint for movement. However, is it a hinge joint? Is it a ball and socket joint? Is it a gliding joint? Like what type of joint is the knee? Go ahead and see what type of movements does the knee allow. Does the knee flex and extend? Does it abduct? Does it rotate? What type of movements, and then what kind of joint is the knee? All right, and now we're going to be diving deeper into muscle structure and hierarchy. So the muscle here, breaks down into various components. So you start off with the skeletal muscle here, which breaks down into these tiny little components here, which is a muscle fascicle. And that muscle fascicle breaks down even further into muscle fibers. So it's composed of all these different muscle fibers. And now the muscle fiber breaks down even further. So now we have this muscle fiber here. It breaks down even further into myofibrils and then sarcomeres. So you have the myofibrils here, and then these myofibrils, if you examine those further, you see these sarcomeres. So sarcomeres are, one sarcomere is dictated by what's called a Z line. So these are the Z lines within the myofibril. And so this is one sarcomere within the myofibril. The sarcomeres is where you have those protein elements of myosin and actin. And this is where you're going to have the contraction happen within the muscle itself. So we got to have the muscle. So we got to have these myosin. You can't see it. My gosh, I'm so sorry. My picture's in the way. But these thick filaments called myosin right here in the middle. And then we have these like long bars coming out from the side here. These are these thin actin myofilaments or actin filaments. And so what they have to do, they have to come together and then connect, and then they create a cross bridge. And so once they come together, they grab a hold of each other and pull, they shorten the muscle by bringing each other closer and closer until the muscle shortens and creates a contraction. So here is a description going over the relationship between the length of a muscle and then the tension that it creates. So the length of the sarcomere determines the amount of force it produces and thus the amount of tension it experiences. So the bigger the sarcomere, the more force or the more potential force available. And the force generated is, again, generated by those tiny actin-myosin filaments that I went over that are within those myofibrils. And so when the sarcomere is stretched or too short, the degree of overlap is incomplete. However, when the actin and myosins have maximal overlap, the highest number of cross bridges can be formed. You're going to have the highest number of force production, but then it's going to plateau and then it's going to eventually go down. And so during muscle hypertrophy, so when we are training, we are trying to generate or trying to train that muscle, train that portion of the body to generate more force to become stronger. That happens by improving your body's ability to generate more actin and myosins, because those are protein filaments, and so your body's ability to generate more of those. So we have more cross bridges. You'll have the muscle itself thickens because there's more protein filaments within that muscle, and so you're able to generate more force when there's more actin and myosin. When you have muscle wasting, so as we get older or different phases of life, if you are not prioritizing either daily movements that force your body to contract and have those reactions, or if you are not strength training, then you are going to have a loss in those actin and myosin. So hypertrophy occurs when you have greater actin myosin being produced than what's decaying naturally. And then different types of muscle contractions. So we have concentric when the muscle is shortening, and then we have eccentric when it is lengthening under tension. Then we have isometric when there is no length. So here is another illustration of this. So concentric, you'll see the muscle for, this is an example with the bicep curl. The bicep curl, the muscle is going to shorten when you bring the arm up. So it's going to shorten. That is concentric contraction. When you're having to fight resistance, fight gravity to bring that weight up, the muscle is contracting to generate that force, or shortening to generate that concentric force. And then bringing that weight down. So you want to be able to control the descent, bringing the weight back down. Because if you just go with gravity and just let it fall down, that could produce injury and produce risk. So your body has to be able to control the descent, and it does that through eccentric contractions. So it's being able to generate that tension, control that movement by lengthening. So being able to bring that weight back down, the muscle is now going to lengthen back to that starting position. And then we have isometric, where there is no movement. So just being able to hold that weight at a 90-degree angle by your body, being able to hold that weight against gravity, not letting gravity win and bringing it down, being able to hold it outright, having isometric, so you're generating tension within the muscle where it's having to control to maintain this position, but there's no movement in the joint itself. You see isometric contractions again with planks. So you're generating that tension within your core, within your abdominal muscles to hold that position, but there's no joint movements. And then we have functional roles. So we have the muscles themselves have all different types of functional roles. So we have agonists, antagonists, synergists, and stabilizers. So antagonists are what's known as your primary movers. Those are what's generating that force to create that movement occurring. So they're the muscles that are most involved and contribute significantly to the joint muscles, and then or to the joint movement. And then your antagonists are muscles that have the opposite effect, or they're known as the contralateral muscles and are located on the opposite side of your agonist. So for my example here, So for my example over here, we have extension and flexion of the biceps. So the being able to flex your biceps, or being able to flex your elbow, your biceps are the agonists to bring that elbow up, while your triceps on the opposite side, on the contralateral side, are the antagonists. They're having to lengthen, having to relax to allow the movement in that joint. We can't have the biceps and the triceps shortening at the same time. That's going to create no movement in the joint. So we have to have one shortening while the other one is lengthening to allow the other to move. So again, the triceps are the antagonists, where the biceps are the agonists in this particular example. And then we have our synergists and our stabilizers. So our synergists are known as guiding muscles, so they assist the action of the agonists, but are not the primary movements. They are for refined movements and preventing undesirable movements or actions. So for this example, again, of flexing the elbow, the bicep curl, so the biceps brachia is your agonist. And sorry, my picture's in the way here again. So the biceps brachia is your agonist, while these smaller motions, smaller muscles are supporting the area and still helping prevent undesirable results. Undesirable movements at the joint will be your brachialis and your brachioradialis within this area. And then we have stabilizers. So stabilizers are also known as fixators. They surround a joint or body part to fixate, to stabilize, so the other body segments can exert force and move. So you see the stabilizers most often in the proximal joints, so the ones that are going to be closer to your trunk. So the more distal joints can have that movement to prevent that, or can have that desired effect. So for example, when we are trying to do a bicep curl, bring in your arms up and in. To be able to move the elbow, to move that arm, we need our elbow to be stable and locked. We can't have the elbow also trying to raise up when we're trying to lift up a bicep curl. We need that joint to be stable and fixated. So the muscles surrounding our scapula and our glenohumeral joint is going to stabilize and fix this joint in place. So our more distal joint, our elbow, can provide that desired motion that we're trying to achieve. All right, so applying to what we know so far to an example. So with a squat, you have two phases. You have the descent and then the ascent. So when you're lowering and then rising. So for the quadriceps specifically, when you are doing the squat position, when you are having to lower down into that position, your quadriceps have to lengthen. So eccentrically, they have to generate tension to support yourself as you're lowering down into that squat position. And then during the ascent, they shorten and to help you stand back up, to help with that hip flex or that hip extension. So they're going to have that concentric contraction during the ascent. All right, and knowledge check. So during the lowering phase of the curl, so the bicep curl, so during the lowering phase, what type of contraction is that based off what we've gone over so far? All right, and now we're getting more into the neuromuscular side of things. So we're going to start going over the motor neuron and the motor unit. So a motor neuron and the muscle fibers it innervates are considered what a motor unit is. So again, a motor unit is the motor neuron, which is, let me get my little pencil here. So this is the motor neuron, and then this is the muscle fiber that it's innervating. So a motor neuron can innervate different muscle fibers. It's not a one-to-one. It can have 2 to 300s to 1 motor neuron. And so that whole unit, the motor neuron and all the fibers that it activates, that it innervates to stimulate a contraction, is considered a motor unit. All right, so with these motor units, they really have an all or none principle. So the motor unit is either going to contract fully, it's going to stimulate that motor, the muscle fibers to generate the actin myosin cross brakes to stimulate that contraction, or it's not going to contract. So it's either all or nothing. There's no partial contraction of the fibers within a motor unit. Again, I'm so sorry, I'm over this. So the motor unit, so the activation occurs once the stimulus threshold or once the threshold stimulus is reached. So not all motor units share the same threshold. Some, like the smaller, slower twitch units have the lower threshold, and so they will fire first. So if there is stimulus being traveled into a certain area of the body, or to move, to walk, your smaller, slow twitch motor units will fire first and stimulate to perform the action, the movement that is being desired at the time. And then your large, fast twitch motor units have a higher threshold and are only recruited when extra power is needed. So, let me go to, here we go. All right, so why the all or none principle matters. So force is not graded within a motor unit. It's graded by recruiting more motor units and increasing firing frequency. So the amount of force or tension a motor can generate is dependent based off how many motor units your nervous system can innervate, can stimulate to start a contraction within that muscle. So for example, during a heavy squat, each recruited motor unit contracts completely, and more comes from recruiting additional motor, and more force comes from recruiting additional motor units. So for example, the bicep is estimated to have anywhere from 700 to 800 motor units. And so your body's ability to generate more or stimulate more of those motor units, you can stimulate more force in the bicep muscle. And so that comes with training. So in addition to the hypertrophy of the muscle, where we can increase the protein synthesis of the actin and myosin, we enlarge the muscle so there's more ability to generate force. But we can also increase the nervous system's response so it's more efficient and more effective, where we can innervate more motor units to innervate this muscle so we can get more force. So we can try to maximize that position with training. So again, a motor unit consists of a single motor neuron and all the muscle fibers it innervates. Alrighty. Okay, and this is kind of summarizing that a little bit again. So an increase in number of motor units involved in contraction increases the contraction force of the muscle. So again, if we're able to increase the amount of motor units that your body can innervate, then you're going to have an increase in contraction or increased force when that muscle is contracted. And there is a threshold stimulus. So the threshold stimulus is what is needed to be reached to activate a single motor unit to produce a very small force of contraction. Submaximal stimulus activates multiple recruited units or motor units to produce a greater force of contraction. And then, as I mentioned earlier, smaller and weaker motor units are recruited first, and then your larger and stronger muscle units are added as needed. And maximum stimulus activates all motor units to produce maximum contraction force available within that muscle. So like if you're trying to do a 1 rep max in like doing a squat, doing a 1 rep max. So doing the most that you can handle. You're trying to like maximize your motor unit capabilities, trying to reach that maximal potential with that stimulus. All right, and rate coding. So rate coding refers to the frequency of motor neurons firing. So how fast are these motor neurons innervating the muscles? They're innervating the muscle fibers. So once they're recruited, so once these motor units are kind of turned on, they're reaching that threshold, that stimulus that's needed. So how can we also increase force? By firing more frequently. So faster firing increase or results in a greater force production as well. So recruitment versus rate coding. So recruitment is activating more motor units. You're recruiting more people, more units. And then the rate coding is increasing the firing frequency of active motor neurons. So recruiting versus increasing the stimulus or the frequency needed. So again, how many units there are versus how fast they're being fired. All right, so the summary here. So Muscle force production is regulated by the all or nothing principle. So motor units are either going to fully contract or not at all. Muscle unit recruitment, more motor units activated equals more force. Faster firing frequency results in a greater force. And so the big picture, why does this matter? So movement comes from the structural pieces, so our muscles and their role, what they're able to do, their capability, and then the neural control, so our nervous system's ability to have that control to innervate the muscle, innervate the motor neurons, innervate more muscle units or motor units, so that neural control. And then bringing it back to structural kinesiology. So structural kinesiology explains what can move. And then neuromuscular control explains how it moves. The nervous system selects which motor units are activated, how many they activated, and how rapidly they fire. And through training, that nervous system, that function becomes efficient becomes more efficient and more capable of doing more. All right, so knowledge check. Neuromuscular, how do we increase force output? So what are the ways to increase that force production? Sorry if you hear my dog in the background, by the way. All right, so kind of overviewing what we've gone over so far with Module 1. So from this point, you should now be able to explain what is structural kinesiology, describe the anatomical position using proper terminology, identify the plane and axis of movements for a squat, a lateral raise, and a trunk rotation. So again, your sagittal, your frontal, or your transverse plane. Explain how muscle structure influences function, and then distinguish the difference between concentric or eccentric contraction, and then recruitment versus rate coding. So being able to distinguish the difference between those. All right, in Module 1, so being able to apply this, you can now understand, again, anatomical terminology, planes of axis of motion, bones and joint classification, muscle structures and contraction principles, neuromuscular force regulation. All right, and then preparing for Module 2, we will now start going more into like what specific joints and specific movements and the roles that this plays. So going from general principles to joint-specific analysis within the next module coming up. All right, and again, here is our reference. So as always, please let me know if you have any questions about this material, about what's being covered with the modules. You can always email me or ask to meet. Would love to go over this. This is some really exciting stuff, but please let me know if you have any questions or concerns about anything. All right, but see y'all around.